In the last lecture, we discussed about how to calculate the volumetric flow across a membrane. So Q would be the surface area if you get a constant water flux across the membrane, you can use this multiplication. So surface area multiplied by Q water, which is surface area multiplied by the LP, which is the conductance in porous medium multiplied by delta psi, which is the chemical potential difference of water across the membrane. And here we have LP. Now we want to estimate the hydraulic conductance for porous media. So let's look at what happens in blood vessel. So let me draw this in blood. So you have endothelial cells lining up here, and I'm exaggerating the gaps. So you have those tiny gaps between neighboring cells, and they can allow water and small solids to pass through. So this is one way of looking at it. If you look at it from the top, then you will see a circle, some maturing cells. Okay, so these are endothelial cells. And you will also see gaps here. It's the same gap there. So this is the geometrical features or like a visualization of how the gaps between endothelial cells can contribute to some pores, and that's what we call porous membrane. So you can treat the epithelial wall as a porous membrane. Now let's be more general. So let's see you have a membrane. So this is the L is membrane thickness, and the S is the surface area of the membrane. So let me write it down here. Membrane thickness. The S is membrane surface area. And you have pores in it. So if you look from the side, you will see look like this. And then if you look on the side, you have those types of pores. I'm just drawing three. And you know the idea. So you have multiple of these pores on the membrane so that you may expect it will. Now, given this picture, so this flat membrane is a generalized idea of the blood vessel. So suppose like you cut your blood vessel and you stretch it and you get a membrane like this. Now let's consider two scenarios. One is as I draw on this illustration, your membrane has pores which are cylindrical. So each pores, it's a tiny cylinder. So it's cylinder of this pore. So this is one pore. So for this pore, the length is L because this is the thickness of the wall, and the pore radius, we use capital R. So now let's consider this scenario. We have hydraulic conductance in cylindrical pores. So for this cylindrical pore I just draw here, recall from what we learned from last module of the blood flow in blood vessels, and we had I had Poisson law. So we call Poisson. It tells us the volumetric flow rate. It means the Q across one single pore is pi R to the power of 4 divided by 8 mu L delta P. So now in this scenario, delta P is the pressure difference across the membrane. So delta. And the mu is dynamic viscosity of the water or any solvent that you are interested in. So let's see. L is both the membrane thickness and the length of the pore. So let's start with this Poisson's law for a single pore. Now let's think about a real membrane. You may have more than one pores, or you actually may have a lot of these pores. So how do you account for this? And let's see for a membrane. Let's say you have n pores, n is the number of pores. So now this Q, what I wrote above is the Q across one pore. If you have n pores, then you would have n multiplied by this Q would be the total volume flow rate across the membrane. And now let's also think about the size or the shape, the geometry of the pore. So here, what I draw here is like a straight pore. But if let's look back. So if you look at the distance, well, the gap between cells, so this gap. So if you have water going through this path, you can see this path is not a straight, or maybe this path is also not a straight. So if it's not straight, then the effective length of the pore is longer than the thickness of the wall. So you may have a correction factor to consider this. This is what we call the characterized density. So this porosity factor. So it is always greater or equal to 1. So this L is membrane thickness. or the length of the pore for straight pore, or the length of a straight pore. So now we can define L R, let's call it tau multiplied by L. This is the length of a non-straight pore. Okay, now let's consider the length factor and also the number of pores. Let's do the last change is we change delta P into delta cosine for osmolarity. Difference across the membrane. So with these changes, we have a new expression for Q. So our Q is N is the number of pores multiplied by I R cubed. Now in the denominator we have 8 mu. Now we use the true length, which is tau multiplied by L, and multiplied by the driving force delta psi. This is the volumetric flow rate across the membrane. Volumetric flow rate across the membrane, not a pore. Okay, now let's continue to develop our equations. Now let's define AP as the total cross-sectional area of the pores. Define AP, A sub P as the total cross-sectional areas or area of pores. So by definition, we have AP equals to N pi R squared. With this relation, we can rewrite Q rewrite the expression of Q in terms of AP. So now we get Q equals to A sub P R squared divided by 8 tau 8 mu tau L. So we can look at this equation, this expression for tau, and compare it with the expression that we had from last time. This is the Q from sort of the physical definition of from the driving force. You have LP is membrane conductance. If you compare these two relations, you can get the following, which tells us AP APR squared divided by 8 mu L delta psi equals to S LP multiplied by delta psi. Now this is the equation that we can rearrange to solve for LP, solve for the hydraulic conductance. So you can just do the rearrangement. Solve from ULP equals to A P divided by S divided by R squared 8 mu tau L. Okay, so we solved our hydraulic conductance. So the purpose of this lecture is for us to estimate the hydraulic conductance of a membrane with pores. Now this is one estimation. Now let's look at the ratio AP divided by S is the ratio of pore area area. So now we can define epsilon equals to AP divided by S. This epsilon is called the porosity. Porosity. The membrane. So with this expression for porosity, we can write LP equals to epsilon R squared H mu tau L. So this is the hydraulic conductance of pores of membrane with cylindrical pores. This is the hydraulic or permeability of membranes. Now let's look at um let's look at an example. So let's calculate the filtration flow rate of a pure fluid of 100 centimeters squared membrane. Assume viscosity 1.8 times 10 to the minus 3 pascal second. The porosity of the membrane 40%, and the thickness of the membrane is 500 microns. The pores run straight through the membrane. And these pores have a radius of a given number. The radius of 0.225 micron. Pressure drop applied across the membrane is given. Is 517 kilopascal. Okay, we needed to find the Q. So in order to find the Q, you needed to know the membrane conductance. So let's first find the membrane conductance. Or maybe let's put it the way of how we solve it. We want to find the Q. Well, you can think about how Q is expressed. The Q is the SLT delta psi. Since it's a pure fluid, we don't need to consider osmolarity. So that means it's LP delta T. And we know the surface area of the membrane is given. So we need to find the LP. So that's why we want to find LP. LP is conductance. So we just learned how do we find this. It is epsilon r squared divided by 8 mu L. Let's see, do we know everything here? Yes, we know. We are given the porosity, we're given the size, the radius of the membrane. We are given the length of the pore, the viscosity, and also the pore stretch. So we just plug in a number. 40% is the porosity 0.4 multiplied by the radius squared. It's about 8 multiplied by mu. Mu is 1.8 times 10 to the minus 3 times per second. The tortuosity is 1 because it's a straight force. And then we have the length of the pore, each pore. Okay, you can see that if you do work on the number and also work on the units indeed give you something which is meter per second. This is a unit of the hydraulic conductance or permeability of a. So the number is 2.8 times 10 to the minus 9. Okay, now let's to calculate the Q. Q is LS. Delta P. Okay, the area it's given, let's see, it's given in centimeters squared. We need to convert it into meters squared. It's 100 times 10 to the minus 4 meters squared. And multiplied by the LP we just found, which is 2.8 plus 10 to the minus 9 second. And then we multiply by the pressure difference, which is 570 times 10 to the 9 times 10 to the power 3 Pascal. So it will give us 14.5 into the power of minus 6 meter cube per second. Now we solved this problem by using or by estimating what is the conductance of the membrane. So let's look at a scenario that the membrane pores are not cylindrical, but they are rectangular slit pores. So this is also like an approximation or estimation because in reality, the gaps formed by the endothelial cells between cells, they may not be that regular. They may sometimes look like cylindrical and sometimes look like rectangular. So now here, let's assume if the pores are rectangular, then how do we find the conductance? So this is Actually, the conductance in rectangular slit pores. And then let's assume the pores the slit pores means they are thin, so the thickness is much smaller than their width. So we have thickness is 2h, the width is w, length is l. So you may wonder why we use 2h as thickness instead of h. This is just a convention when people derive the volumetric flow rate. So recall what we learned in the last module. In this case, the volumetric flow rate across a single pore, rectangular pore, is 2W H cubed divided by 3 mu L multiplied by W, delta P. Now let's do the same thing. Consider the n number of pores, consider tortuosity, and also consider osmolarity. We get a Q equals to N multiplied by 2W H cubed divided by 3 mu L multiplied by delta P. The reasoning is exactly the same as what we discussed for a cylindrical pore. Now let's look at the total area from rectangular pores. It is N multiplied by 2HW. So this is 2HW is the area, the cross-sectional area of a single pore. And then if you have any number of pores, then you multiply by N. So in this case, you can rewrite your Q by using the area. So it will give you A C squared divided by 3 L multiplied by delta psi. Now let's do the same thing as what we did for cylindrical pores. This should equal to S multiplied by the hydraulic conductance of the pore multiplied by delta psi. So this solves for the hydraulic conductance for rectangular slit pores. It gives us AP divided by S multiplied by H squared. And by 3 mu tau L. And this gives us epsilon. Okay, so this is the hydraulic conductance of permeability. Or rectangular slit pores. And again, this doesn't require that H be much smaller than W. Otherwise, the relation will break down. Okay, now you can compare the two expressions for cylindrical and for slit pores. So let's compare. Here. The conductance geometries. One is cylindrical, it's called LP. Cylindrical, it is epsilon r squared divided by 8 mu power L. And then we also have LP for slit. Epsilon h squared divided by 3 mu power. So let's consider a scenario you have a cylindrical cross-sectional area, and you have a slit cross-sectional area. So the height is 2h, and the radius or the diameter is 2r. If you have membranes of pores with this type of geometry, and if they have the same sort of height, or the diameter, well, you cannot really use height for a circular. You cannot really talk about diameter for a rectangular. But let's just say if they are like the smaller set dimension are the same. So if r equals to h, then you can compare the ratio LP for slit divided by the conductance for cylinder. For the slit, you have 1/3 as a coefficient. For the cylinder, you have 1/8. So it gives you a ratio about 2.67. So that means for roughly about the similar dimension, the rectangular pores are more conductive compared to cylindrical pores. And for this reason, when people wanted to achieve like higher conductance for the same minimum dimension, people may choose cylindrical pores. And also for a lot of the gap between the endothelial cells, many of them do look like rectangular instead of cylinder. Okay, now let's see. So let's look at two exercises. So since my pen isn't working out very well right now, I'm not going to write down. I think I'm going to copy and paste the following statement. Let's do one exercise. because this exercise does have several components, I think that's to have. Okay, let's work on this one.